Hello, and thank you for watching my brief talk on an uncertainty-based framework for explaining compulsive behaviors in OCD. OCD is a disorder characterized by persistent intrusive thoughts known as obsessions, accompanied by repetitive behaviors or compulsions aimed to relieve the anxiety from the obsessions. Examples you might think of are people who wash their hands dozens or even hundreds of times a day every time they touch something out of fear of contagion. Or another example, people who cannot leave home because they have to keep checking that their gas stove is off. Um, and when it comes to figuring out exactly what the mechanism is behind these stereotypical compulsive behaviors, some things make that difficult. For instance, when we're looking at performance across tasks, there are mixed findings. Some studies found similar performance to controls, for instance, in some kinds of reinforcement learning tasks, whereas others find impaired performance, such as on planning tasks or some working memory tasks, and even better performance, such as on information gathering tasks. And these mixed findings have led to conflicting accounts of what the underlying mechanism is. For instance, one popular account sees OCD as a learning-related dysfunction, in which people who suffer from it cannot represent the true world structure and they learn the wrong values for available options. Whereas a different account sees it as a goal-directed dysfunction, assuming people who have OCD can accurately represent world structure, but they cannot respond appropriately to what they learn and observe. And what I'm going to propose here is a framework in which we're using uncertainty to reconcile these mixed findings and conflicting accounts. Specifically, most tasks studied in the context of OCD look only at local uncertainty reduction, or the bottom half of the graph here. I'm washing my hands because I want clean hands. But in real life, we rarely have these goals floating in the void. Rather, they're part of a hierarchical structure in which a goal such as have clean hands is actually part of I want to wash my hands to have clean hands to preserve my general health. So you can see we have two components here. We have the local uncertainty reduction, by which we keep taking an action, hand washing, until we have checked and we have updated our world representation to say my hands are clean. And then once that happens, we can integrate this fulfilled sub-goal into our global goal. And we can say, okay, now my hands are clean. I'm not going to catch whatever plague is rampant in the world. And I can move on to my next sub-goal. So our hypothesis is that OCD spares this local uncertainty computation, so the bottom half of this graph, but it impairs the integration to global goals, which can still result in having correct representations of the world structure, but you're unable to act in them in a way that's consistent with goal-directed behavior. We tested this using the Archer task, a predictive inference task requiring people to observe data to infer underlying local and global world structure. So in this way, this task is different from many other LCD tasks. In the story that we tell participants, they have to take this archer through a forest to overthrow an evil overlord. The way they do it is they have to correctly predict its position at the end of the task and fire an arrow at it. The way they learn this position is before they face the overlord, they go through regiments of its guards, which we call local information, and each regiment's position is generated from the position of the overlord, or the global information. So as they proceed through the task, they're learning at the same time both the local and the global information. I'm going to quickly show you a video of the task. You can see the archer adjusting its firing position and firing an arrow, and it has missed the current guard. And so it's going to adjust again, trying to take the new data point into account, missed again, and it's going to do it a third time. And keep in mind as you watch this, the archer is required to learn both the local information, so where is the next guard going to be, and the global information. What is this regiment telling me about the position of the overlord overall in order to maximize reward in this task? Critically, you might see here the run button. At any point, the archer can choose to stay or see more guards in the current regiment, or they can run and encounter the next regiment. If they choose to stay, then they're going to see more guards, which will help them better infer the local regiment's position and gain more points. On the other hand, if they choose to run, they can see more regiments, which is going to give them more samples for the overlord's global position. And since they have limited arrows, that's going to lead to a trade-off between the local information and reward and the global information. We model the task with an optimal model that predicts whether the player will stay on run or run based on the action values of staying and running. These values depend on what it has learned about the local and global information. As you can see here, the model relies on Bayesian updating, in which each new sample, shown as the black line, narrows down your previous belief, shown as the blue line, into something with less uncertainty, or the purple curve here. Now, our model makes several predictions. The two most important ones are, in terms of local learning, the more guards you see in one regiment, the more accurately you'll be able to aim at them. And in terms of global learning, the more regiments you encounter, the better you'll be able to aim on the first trial of each new regiment, because you are extrapolating your local information into your global information. And in line with model predictions, when we look at our data with 20 patients and 20 age-matched controls, we can see in local learning, both groups are able to improve their accuracy with the number of guards seen in the regiment. However, when we look at global learning, we see that the model predicted outcome of increased accuracy on the first trial with more regiments encountered is only shown by the control group and not by the OCD group. Similarly, if we look at the correlation between the slope of this line here, so how fast are they learning, and how accurate they are on the final trial in which they're facing the overlord, we see a positive correlation only in the control group and no correlation in the OCD group. And for a very quick additional evidence that the OCD group does not integrate information from local into global, if we look at reducing how much they adjust their aim, which they should do with more regiments encountered, they actually do not show that as the controls do. And the controls show longer reaction times on the first trial of each new regiment and on the overall trial, which suggests that perhaps they are taking this extra evidence into account, which the OCD group is not taking into account. So to sum up, we believe that OCD preserves local learning and uncertainty reductions at the bottom half of this graph, but it impairs integration of local uncertainty into global learning. And this framework can actually reconcile the learning rated and goal rated deficit accounts of OCD. And thank you to my advisor, Michael Frank, in the Frank Lab, as well as Steve Rasmussen's group, and the Butler OCD Research Group, and Tina Bosso, who was in charge of the patient sample we used for this study. Right? Thank you very much.